Okay, hello everybody. Welcome to the first session of the 101 stream. So my name is Harvey Singh. I work at BMC Software. I've been doing sort of DB2, DBA work for sort of over 2 years now. And my co-host of the 101 stream, who's also doing this session today, is Lena. So I'll leave you in Lena's hands.
Well, hello everyone. Thank you very much for joining the 101 stream. My name is Lena Rush. I work at IBM. I'm with IBM for almost 2 years now, and I'm a client technical specialist at IBM. I focus mainly on the mainframe hardware, and yeah, I'm very excited to give you a bit of an introduction to the mainframe hardware in this session. So we wanted to start with just laying out the sessions we have planned as part of the 101 stream. And we wanted to point out 2 sessions in particular. So every Wednesday, so tomorrow and the Wednesday next week, we are hosting a networking session for everyone new to SET. So we are really sad that we can't meet in person, but we still wanted to get to know each other. So those sessions are running from 4 until 5. It's a very casual get together, but it would be nice to see many of you on those sessions. And you will find the links to those sessions in the agenda. Then before we start, a couple of things. If you have any questions, just submit them in the chat window. We should have some time at the end of the session to go through a few questions. We are recording the session, so you will get the link to the recording afterwards. And I have uploaded the presentation slides, so you should be able to download them just after the session. And it would be great to get your feedback on the session. So there are a couple of ways on how you can submit the feedback, but we would love to hear your opinion on how you found the session. Okay. Then let's get started. So the session is an introduction to the mainframe hardware. And the aim of the session is to give you an understanding of what a mainframe is and what makes the mainframe hardware design so special. So let's start with defining what a mainframe actually is. So mainframe is a computer that is used by organizations for critical applications, which require high levels of security, reliability, availability, and serviceability. So mainframe is a computer like your laptop or your phone is a computer. But the architecture of a mainframe is specifically designed to be a great fit for those really critical applications. And in the first part of the session, we will explore why the mainframe architecture is such a good fit for those critical applications. So let's start by taking a look at who is actually using mainframes. And we, of course, right away think about the big banks and the large institutions. But actually, most of us get in touch with a mainframe almost every day. So we get in touch with a mainframe when we get cash or when we make any sort of card payment. So if that's in store or if it's online, we get in touch with the mainframe if we make any sort of insurance claim or if we go grocery shopping. So over 30 billion business transactions are handled by mainframes every single day. And just to put it in relation, there are around 6 billion Google searches every day. So 30 billion versus 6 billion, it's a huge number. So most of the top banks are using mainframes, most insurers, most retailers, and most of the world's largest airlines. So let's have a look for what sort of applications those companies are using mainframes for. And we already said mainframes are for critical applications. So those applications are things such as financial transactions or airline control system or production and inventory control or things like payroll. So those are applications that always need to be available and that deal with very sensitive data that need to be secure all the time and also handle large amounts of data. So we can divide those sort of applications and the transactions that come with it into two types. There are the real-time transactions. So that's things that have to happen right now. That's event-based. So for example, a credit card payment or making a purchase. So this needs to happen instantly. And then there's batch processing. So that's things that kind of summarizes events that happened over a certain amount of time. For example, paychecks or phone bills. And the mainframe is great at doing both of those sort of transactions. Now I wanted to take a quick look at an example of a banking use case. So we said that we would get in touch with a mainframe if we, for example, get cash. So here's how that would work. We go to a cash point and we withdraw some money. So the request would be sent to a mainframe, and the mainframe would then read the data from storage to see if this request can be accepted, if there's enough money, if my balance allows that. It would then update the balance on the database, communicate it back to me, and I would get the cash and I would see the new balance. So this is something that would need to happen instantly and in real time. Then we would have, for example, someone from HR in the central office who's doing payroll. And this payroll process might not need to happen instantly, but it can be something that could be scheduled, for example, happening during the night. And for this payroll process, we'd also request information from the mainframe, which would then go via storage back to the mainframe. And this would be an example of a batch process because it kind of summarizes changes that happened during the previous month. Now, I wanted to give you a bit of context on different types of servers and how the mainframe actually fits into that. So the most commonly used server are rack servers, and they follow an x86 architecture. So as the name says, they come in racks, and usually you would put them into frames, as you can see there on the picture. So on the picture is an example of a server farm and how that would look like. So if you would require more compute, you would just buy additional racks and you would put them into those frames. Then we have the mainframe, which is often referred to as an enterprise server. And the mainframe comes in a configured frame, and we will talk a bit later about the configuration and how that works. But often one mainframe is actually able to do the work of several hundreds of those x86 servers. Overall, a price of a mainframe like this is, of course, much more expensive than having a single of those rack servers, but the total cost of ownership can often be much better because if you reduce complexity, you require less space, less software licenses, and so on. So you're able to run more efficiently on a mainframe because of its specific architecture and its specific hardware. And that's what we will explore in the session. And I keep on saying the mainframe, but in reality, there's not the one mainframe. Mainframes have evolved massively over time. And what all of those mainframe models have in common is a shared architecture. And that's the S390 or the Z architecture. But over the years, they have changed a lot. Just like your laptop or your phone is very, very different from what it was 10 years ago. So before we dive deeper into this architecture, let's take a look at the evolution of the mainframe. So the System 360 can be seen as the first type of mainframe. It was introduced in 1964. And at that point in time, computers were dedicated to a certain task. So there were computers which were dedicated to scientific tasks or computers dedicated to commercial tasks, but there was no machine that could handle it all. So the mainframe was really a game changer because it was the first machine that could handle various types of tasks. And that's also why it's called the System 360. And at that point, IBM made a promise of backward compatibility, meaning that any application written on a System 360 is able to run on future mainframe architectures. And that was really important back then because a lot of effort was spent on developing applications. And what often happened was that a new version came out and all the work that had been done was useless because it wasn't compatible anymore. And by a company investing in a mainframe and by IBM committing to this backward compatibility, this issue could be resolved. Then in 1970, the System 370 architecture was released. And what was very special about that one was the concept of virtual memory. Then in 1990, the System 390 was released. And 10 years later, the Z architecture. And with the Z architecture, you notice right away that there is a change in naming convention. And the Z stands for zero downtime. So you might notice that the gap between those releases are quite big, but this doesn't mean that there were no updates in between. It's just, I didn't list all of them, but within those bigger architecture releases, there were a lot of new generations. So let's take a closer look at what happened after 2000. So the Z release in 2000 was very important because from that point on, the Linux operating system was supported on the mainframe. So we now support Linux for over 20 years. And nowadays, usually every 2 to 3 years, a new mainframe model is released. And the latest mainframe model was released in September of 2019. That's the Z15. And in 2015, IBM released a second mainframe type, and that's the Linux one. And the Linux one follows the mainframe architecture. So from a hardware perspective, it is very similar to the Z15, but it's dedicated to running the Linux operating system. So the operating system support is really the key difference between the Linux one and the Z machine. So on the Z15, you can run ZOS, so the operating system that is specifically developed for mainframes, and you can run Linux. But on the Linux one, you cannot run ZOS, but you can only run Linux. So this machine is still a really great option for companies that don't require ZOS, but still want to have the benefits of a mainframe, for example, the security and the performance. So now I want to dive a bit deeper into this latest model and into the mainframe architecture. So mainframe is made up of Cpc Drawers, which stands for Central Processing Complex, and this really houses the brain of the mainframe. Then we have the I/O drawers and power, cooling, and cabling. But not all of the companies that want to buy a mainframe have the same requirements. So whoever is buying a mainframe can decide how powerful they need their machine to be. They can configure it to their needs. And in the table, we can see how this would work. So based on the number of cores, a certain number of Cpc drawers is required. So if there's a company that needs to have the maximum amount of cores, so 190 cores, and really needs an extremely, extremely powerful machine, they would need to have 5 Cpc drawers. But there might also be companies that require a smaller option. So if they would only require 20 cores, for example, they would only need 1 Cpc drawer. And based on this configuration, based on how many Cpc drawers they need and how many I/O drawers, the mainframe comes in different sizes. So let's take a quick look at that. So here we see the different sizes for the Z15 mainframe. So based on your configuration, you can have from 1 to 4 frames. And today, the mainframe sizing follows standard data center design. So it's standardized hardware design, making one frame 19-inch wide. And this means that the mainframe can actually stand with all the other hardware that follows that standard design in the data center. So it can stand with storage and with the other servers. And when we look back at those earlier models from a form factor, they were different. So they usually had their own area within a data center, but with those newer models, it's a big advantage that they can actually stand with the other hardware in the data center. So now let's go a bit deeper and look at what is inside the mainframe hardware. So here we can see a maximum configured Z15 from the inside. And you might work with an older model, but from an architecture perspective, the key components are similar. So let's start with having a quick look at the naming convention of the frames. So the first frame is the A frame. So if you have a small configuration and you only require one frame, you would only get this A frame. If you need 2 frames, you would get the A and B frame, and so on. So in this maximum configuration, we have 5 Cpc Drawers, and those are in the A and B frame. And then we have 12 I/O drawers, and those I/O drawers are split up over all the frames. We also have a support element, which is at the top, and then power and cooling at the bottom. And now let's take a more detailed look at all of those components. And let's start with the support element. So we know that the mainframe is an extremely high performing machine, but how do you actually operate it? So for that, we have the support element, and the support element are 2 integrated servers, one active and one backup, and they have a workstation to monitor and operate the system. It's a closed system, so you can't go there and just plug something in and use it for a different purpose. So you can only do the work which it is intended to do. But just imagine if every time you had to do something at the mainframe, you would need to physically go to the data center. It would be quite annoying and very inefficient. And that's why we have the hardware management console. So the hardware management console lets you access those support element functions, but remotely. So you can add multiple mainframes to this HMC, and you can also add a single mainframe to multiple HMCs. Now let's have a quick look at the power and cooling. So for the Z15, there are 2 power options. So one is called IPDU, and the other one is called bulk power. And which power option is chosen just depends on the requirements. So the requirements are, for example, how many Cpc drawers, the number and type of I/O units, and which cooling facility is chosen. So for the cooling facility, there are also 2 types. There's air or water cooled. Next, let's have a look into the Cpc drawer. As mentioned before, we can have up to 5 Cpc drawers in the maximum configuration. And in each Cpc drawer, we can have 4 single chip modules, and they are abbreviated to SCM. And on those single chip modules, we have the cores. So there can be up to 12 cores on one of those SCMs, on each of them. And those cores are really the brain of the mainframe. Then we have one system controller chip, and the system controller chip is responsible for the communication between the single chip modules. And then we have the PCIe fan-out slots, which are there for the drawer connection. So the communication from one drawer to another, or the communication to the I/O. And we have memory in each drawer. So there's a maximum of 8 terabytes of memory per drawer. And then there's also the cooling manifolds. Now, let's go one level deeper and let's look at those single chip modules. So the single chip modules are built with a 14 nanometer technology, and there are 9 to 12 active cores per chip. It runs at 5.2 gigahertz, and there are 9.2 billion transistors on one of those chips. That's a really incredible amount of transistors in one of those chips. And comparing it to the Z14, we got around 3 billion more transistors on the newer version. Each of the cores has its private level 1 and level 2 cache. And then there is the on-chip level 3 cache. And that is responsible for the communication within the cores and memory and I/O communication and the communication with the system controller. And what is new with the Z15 is the on-chip compression. Before that, we had compression cards, and they would go into the I/O drawer. But by bringing it to the chip level, you can make it much faster and much more efficient. And we also have the on-chip cryptography. And it's really the combination of this on-chip compression and the on-chip cryptography, which makes the concept of pervasive encryption possible. So pervasive encryption meaning that you really can encrypt all of your data, that you don't have to select certain amounts of data which you want to encrypt, but that you can encrypt everything. Of course, increase security a lot through that. And by having this on-chip compression and on-chip cryptography, you can make it quite efficient. So all of the mainframe processors within the Cpc Drawer are, from a physical perspective, exactly the same. But from a logical perspective, they can behave differently. And this is dependent on how they are configured. So they can behave like processors in your laptops. So they are called CP, central processors. This means that those processors can do all kinds of work. Then we have IFL processors. So they are the integrated facility for Linux. And those are specifically for running Linux on the mainframe. You can also run Linux on the CPs, but there are, from a licensing perspective, there are cost advantages of running Linux on the IFL. And that's the same kind of concept that's also valid for SIPs. So SIPs stands for Set Integrated Information Processor, and they are specifically designed for, they're specific for running Java and DB2 workloads. So you don't have to run that workload on a CP, but you can offload it to run it on SIPs, and also has some cost efficiency advantages there. Then we also have the ICF, which stands for Internal Coupling Facility. And those are necessary if you want to have a high availability configuration of your mainframe. And that's something we will talk about a bit more in detail later. So those 4 types of logical processes are configurable by the organization that is using the mainframe. But then we also have 2 types of logical processors which are required by the system. So we have the SAP, which is the System Assist Processor. And the SAP helps link between the CP and the I/O. So instead of the main processor having to worry about shuffling the data back and forth and all of the I/O processing, the SAP processor handles all of that, and this can really speed up things a lot. So it lets the CP focus on business applications and frees it up from the I/O processing. And this is a key differentiator from the mainframe architecture to, for example, the x86 architecture. And then we also have the IFP, which is the integrated firmware processor, and those are used for system operations and management. All right, so now we have seen some of the key components of the mainframe hardware, and we know that it's a quite complex machine, so physically quite big, with a lot of processors, and it has a lot of I/O. So the question is, how do you actually manage it, and how do you make it run efficiently? And this is where the concept of virtualization comes in. So virtualization basically means that you can take bits of the physical resources and you can build a separate system with them. So those separate systems are called LPARs and stand for logical partitions. So this system, an LPAR, is logically completely separate, even though it still runs on the same physical machine, so the same physical mainframe. So you can decide what sort of operating system you want to run in an LPAR, and you can also decide how many resources an LPAR should get. So you can decide if resources should be shared between the LPARs, or you can dedicate certain resources to a specific LPAR. To manage all of that, you require a hypervisor. And the type 1 hypervisor that manages those physical resources is called PRSM or Prism. And Prism is dividing those pre-computing resources, like the physical resources, into logical computers, which can go to the LPARs. So it is implemented within the firmware, and it's part of the base system. So Prism fully virtualizes the system resources, and it runs without any additional software. So through Prism, you can create up to 85 LPARs. And as I said, on those LPARs, you can run a mix of operating systems. So here, for example, ZOS or ZTPF or Linux. And then we also have the type 2 hypervisor. And with the type 2 hypervisor, you can virtualize even further. So those are software hypervisors, and those hypervisors run inside an LPAR. So we have ZVM, which you can see here, and ZVM is the IBM Z proprietary server virtualization, and that's completely integrated into the full stack. And then we have KVM, and KVM is the open source choice. So if you run Linux workloads and if you don't have any experience with ZVM, then KVM might be a good choice for that. So now let's take a closer look at the I/O drawer. So this is a photograph of the I/O drawer, and there are 16 slots. And this is really where all of the input and output devices live. So for example, your crypto cards or your network cards, compression cards. So you would, for example, communicate via FICAN through the I/O drawer to storage or to your local network. So this I/O drawer is really your connection to the outside world. And now let's also take a quick look at the input and output operations and the I/O subsystem. So data which you, for example, have stored on disk or tapes has to be transported into memory before it can be processed. And after processing, the data has to be transferred back to its destination. And this movement is an I/O operation. And in the mainframe, there is an input-output subsystem or I/O subsystem. And the purpose of this is to relieve the processors of the task of communicating directly with the I/O devices. We said earlier, we talked about the SAP processors earlier, the system assist processors, and they are handling the I/O processing, freeing up the CPs. Then we have channels, and those channels are the links between the LPARs and the physical ports on the I/O cards. And then we have control units, and those control units are attached to a channel path, and they are what actually is driving the devices we are connecting to. And those dedicated control units are really good at handling devices like disk or tape. And this means that the mainframe operating system doesn't need to worry about it. So it frees it up to actually focus on its primary tasks. And then we have the input and output devices. So what you actually want to connect to. And I don't want to go into too much detail here, but just the key benefits are that the I/O subsystem helps with the I/O offloading from the processor and freeing up the mainframe operating system, which can then help it focus on the important tasks. The link from the logical to the physical helps it in terms of requiring fewer resources, and it also simplifies this disaster recovery. So I said earlier that system set or IBM set, the set stands for zero downtime. And we mentioned at the beginning that organizations are using mainframes for their really critical applications. So this is where the concept of RAS comes in. So RAS stands for reliability, availability, serviceability. Yeah, those three things. So here are a couple of factors which are contributing to RAS. So for example, how reliable is my hardware? Is it prone to human error because it's really complicated to handle or it's easy to make mistakes? How available is my system? And what happens in the case of a disaster? What happens if the physical data center goes down? Do I have other machines that can take over? Or is it very complicated to connect that machine to other machines? Or the factor of serviceability. So does the machine kind of give me notice before a failure happens? Is it easy to detect what is wrong? How easy is it to fix it? And in the case that I have to actually make some sort of update or I have to fix something, can I keep my operations running or do I have to take everything down? And all of those things contribute to how reliable and how available and how serviceable a machine is. And since this is really a key concept in the design of a mainframe, there's a lot of focus on that. And I want to go into a bit more detail how the hardware is really supporting this concept of RAS. So every component within a mainframe is having a decade-long mean time between failures. So they have all been extensively tested and they only get approved to be used within a mainframe if it is assured that they have this sort of mean time between failures. So the foundation of the hardware components which are built into the system are very, very solid. Then we have tons of redundancy built in. So you will look at it on the next slide. But for example, when we talked about the support element, there are always one active and one backup. So you try to avoid single point of failures to make sure if there is some sort of failure, another part can take over. Then also the hot swap capability. Is that possible? So for example, if there was a hardware failure, so if one core one single chip module would actually fail, is there another one that can take over? And would there be any sort of downtime? So with IBM Z and Linux One, the main goal is to avoid that sort of downtime so that it's possible to take over without actually losing any sort of data and being available and staying available. And the system out of the box comes already really very resilient. But of course, there are always enhancements and always add-ons that can make the entire system more available and even more resilient. So I want to take a quick look with you at the concept of redundancy and how the redundancy is built into the system. So here we can see the Z15 and a few examples of this sort of redundancy. So we have redundant power supplies and power cabling. We have the redundant support servers. We have redundant cooling. So basically, all of those things are designed with the concept of redundancy in mind to avoid a single point of failure. So if there's a hardware failure within the machine, other parts can take over. Okay, so this kind of shows how the system itself is resilient. But what happens if an entire data center goes down, or if there's a natural disaster and the entire machine goes down? So there's not one part of that physical machine that can take over for another part. This is where the concept of clustering and Sysplex comes in. So you're able to create a cluster of mainframes to then achieve the highest availabilities for your applications. And this is what we call a Sysplex. So a Sysplex is an active cluster of servers. So basically it's a group of ZOS operating systems which are working together, and they are able to jointly use hardware and software and components to achieve that high availability workload processing environment. The Sysplex can be within a data center, but very importantly, it can also connect systems in separate data centers. And that's where the geographically dispersed parallel Sysplex or GDPS comes in. So you basically have one entity which is running all the work, and that is the Sysplex. Even though you have many physical mainframes and you have separate LPARs, you can just refer to it as Sysplex. So you hear people referring to it as the Sysplex. And the most common form of a Sysplex is the parallel Sysplex. And what is special about this configuration is that instead of needing every system to be connected to another system, you have the concept of a coupling facility. And the coupling facility is basically a special type of LPAR that you bring up, and you would usually have some backups of that coupling facility LPAR on other mainframes as well. And this coupling facility then handles all the complexities and the overhead of those systems working together. So this really then ensures the communication of the members of the Sysplex. And the main benefit of this is, of course, that you remove single points of failure. So if a natural disaster would happen and if a data center would go down, you have other locations that can take over, and you would avoid downtime and you would avoid loss of data. Yeah, so another thing where the Sysplex is very, very important for is something called the rolling IPL. So IPL standing for initial program load, and basically meaning booting up an operating system within an LPAR. So in a parallel Sysplex, you do not require all of the systems to be up and running for the Sysplex to function. So if you, for example, have 10 LPARs, it's okay to bring 2 LPARs down, update them, and then once the update is done, to bring them back up to the Sysplex. And during the time the 2 LPARs were down, the entire Sysplex was still able to function perfectly fine. And this capability allows us to switch out entire physical machines without the Sysplex going down and with having continuous availability. Now, I also wanted to quickly talk about scalability. So we have mentioned that organizations which decide on purchasing a mainframe have the option to configure it to their needs. So they can decide how many cores they need, how much I/O they need, and so on. But capacity demands can, of course, vary. So thinking about Christmas, the people buy much more with their credit cards and transactions go up. Or if you think about COVID, we pay way less with cash, but there are more credit card transactions. So companies might notice that they need more capacity. And this could be for a month, or it could be something permanent. And there are options for that. So there are things which give them temporary capacity, which can be activated remotely. And there are ways to add additional permanent capacity. And you might be able to add permanent capacity also remotely by just activating cores which are physically already in the system, but which were not activated before. Or if you want to have much more permanent capacity, you might need to add another Cpc Drawer. And this sort of scalability is really a big differentiator of the mainframe architecture to an x86 architecture. Because when you think about it with the x86 rack servers, if you would need to add additional compute, if you need more compute, you would go to the data center and you would add another rack server. Versus with a mainframe, you have the possibility to actually activate more resources remotely, which is activating cores which are already in the system, or you can add more resources physically in the same machine. So yeah, you can actually, with this remote capability, you can grow your existing system quite a lot. So we have now talked a lot about the hardware, but I also wanted us to take a look why mainframes are important in our organizations. We know that they run critical applications, but I'm sure that we have all heard that mainframes are a legacy and that companies want to move to cloud and all that. I find it a bit strange because the new mainframe models are a great, or actually perfect fit for the cloud. So what we at IBM, for example, use our Linux 1 mainframes for is the HyperProtect cloud. So that's a public cloud, and it works just like a public cloud, but it actually runs on mainframes. So it's specifically for workloads that require extra high security. And we can use all of the benefits of a mainframe, which we have already talked about. So all of the benefits of a mainframe architecture. So you can consume it like you would consume any other cloud. But the big advantage is that it's extremely scalable and extremely powerful. So you can really host a massive amount of containers on one physical system. So you can host up to 2 million containers on a single machine. And yeah, this of course depends on how big those containers are, but it just shows how powerful and scalable those machines are. And through the mainframe architecture and through that concept of virtualization, which we have talked about earlier, you're also able to separate your guests really well. So if you were a cloud provider and you would have different companies running on that machine, you could separate them extremely well. And actually, mainframe offers better separation of the LPARs than air-gapped. So a separation better than what you would achieve with physically separate servers. Now, those boxes are extremely powerful. And because they are so powerful, we can actually consolidate hardware. So we are able to consolidate less powerful servers, for example, x86, and we can run the workload of hundreds of x86 servers on one mainframe. And this can save costs. But what I really find important is that it actually can make data centers much more energy efficient. So data centers consume a lot of energy, and they do have quite a big carbon footprint. So just imagine replacing hundreds of servers with 1 or 2 mainframes. This can really have a massive impact. So it can help reduce floor space. It can reduce energy consumption, and it can reduce the overall carbon footprint. And I think this is really a key to actually enable sustainable computing. And now the last point I want to mention is security. So we know that historically we needed this highly secure platform, for example, for those critical banking applications. And of course, we still need this platform for those critical applications still today. But a lot of stuff is happening in the area. So for example, new forms of money emerging, just thinking about cryptocurrencies. And for applications around those cryptocurrencies and around keeping those safe and secure, actually the mainframe is a great fit. So security is such an important factor of the mainframe design, and it spans all from the hardware to the firmware to the software, all of it. And we know how important it is, right? We all know threats are increasing and all that. But the latest model really offers incredible tools to protect against the threats. Just for example, thinking about pervasive encryption, being able to encrypt all of your data, or now even the fully homomorphic encryption. So actually being able to compute on encrypted data. And there's just so much research and development going into this to make sure that the mainframe is perfectly equipped to protect against future threats. So yeah, that's why I really think it's a very, very important platform, extremely relevant, and yeah, very, very excited to be in this field. So with that, I'm at the end of my presentation. Thank you very much for listening. And then I would hand over to you, Harvey.
Okay, thanks, Lena. Yeah, so just before we finish, we've got a question in the chat from Marcus. Does each chip have its own compression cryptography?
Sorry?
Does each chip have its own compression / cryptography? I think we covered it a little bit on one of the slides later on.
Let me go back to that one. So yeah, that's something actually which covered here. Yeah, it's on each chip. So you have on-chip compression and on-chip cryptography. And it's really that combination that makes it very special. Because through that, you're then actually able to really use the encryption possibilities since you compress the data first.
Okay, yeah, brilliant.
Okay. Then I would just go back to the last slide here. So here is the QR code for the feedback. It would be great to get your feedback on that. And also another reminder to join our networking session tomorrow from 4 until 5.
Brilliant. Thank you. Thanks, Lena.